どうも、勝手に電力2.0で始めたいと思います。今日1290回目というところで、実際にこの IESR っていう新幹線から出しているところの、資料の中で、ルーフトップ関係のところがあったので、このあたりですね、少しお話をさせてもらおうかなと思っています。Despite kept being overlooked, better transparency is crucial to put upcoming Rooftop PV regulation to success ということで、この Rooftop PV の、レギュレーションをどうやってやっていくかみたいなところですね。この Rooftop Annual Capacity Addition というところで、実際にどんどんアディションっていうのはちょっとずつは増えてるんですけど、まだまだ全然この太陽光のルーフトップが少ないんですね。Besides, ever stagnant national strategic project to install 3.6 gigawatt of rooftop solar in 2025. Unfortunately, これ実際に3.6ギガワットっていう年間で見てると、実際日本がもともと5ギガワットぐらいどんどん増えてるので、そういう意味では少ないんですよね。Unfortunately, there is no concrete plan to incorporate rooftop solar into Indonesia's energy transition strategy. The latest RUKN draft is no exception, not including any specific measures for rooftop solar. Consequently, only around 100 megawatts of rooftop solar is installed as part Q2 2023, falling far behind the 900 megawatt target in 2023. Major slowdown apparent in the residential and business sectors, with a 29% and 6% decline in capacity addition in 2022 compared to 2021, respectively. This is mainly driven by 15% capacity limitation imposed by PLN's intellectual circular. The industrial sector, however, does not experience the same hit by the capacity limitation, with 132% increase in added capacity in 2022 compared to 2021. This growth rate is driven by corporate sustainability initiatives that requiring them to purchase green electricity directly ということで、産業のところ、インダストリーだけが増えてるってことですね。MEMR Regulation 26, 2021 initially showed promise of the first one export-import scheme with a bill saving credit for up to 6 months, including electricity bill savings and first payback period. However, this regulation was immediately countered by capacity limitation by PLN, and 1.1 net metering did not come to pass. Thus, the upcoming revision attempts to find the middle ground with PLN on the system capacity concern. Electricity export to the grid is no longer allowed, and the installed rooftop solar capacity is allowed to go beyond 100% of the installed electricity capacity as long as installation quota remains. The additional revision also exempts the need or capacity charge. As a result of the upcoming revision, the residential sector will be highly unfavorable for grid-connected implementation with zero export scheme due to high curtailment in daytime, reducing their potential electricity bill saving by 40% compared to the net metering scheme stipulated by previous regulation. The impact of the net export scheme on commercial and industrial consumers, however, remains minimal. However, the upcoming quota-based system does raise a few concerns about the quota determination transparency. This determined quota is submitted by PLN and or other business licenses holder based on their own assessment and will be updated annually. Consumers are then welcome to submit their installation application only in January and July, which are also deemed insufficient. MEMR could assign a technical third party to ensure accountability on quota determination, as well as loosen up the installation application period. Another thing to note is the certainty of the transitional period for existing rooftop solar users, where they are bound to the previous version of the regulation for up to 10 years. With the expected increase in RE share, the flexibility of power system has become more relevant than ever. まさにフレキシビリティの問題が出てくるってことですね。この後に見たように太陽光の影響がめちゃくちゃ出てしまうってことですね。With the expected increase of VRE in energy share by 2030, Indonesian power system needed to facilitate more flexible and responsive power networks. Flexibility requirements have been estimated based on the residential load curve. This is defined as a load that can be served by dispatchable technologies and is derived by VRE's generation from the demand curve. Europe Commission Directorate General for Energy. The residential load curve indicates which part of the demand needs to be met by flexible technology, thermal generation unit, hydropower storage, and other renewable energy sources. A nationwide hourly operation for the specific week in 2030 was modeled by IESR with JETP pledge as the objective. The hourly Java Valley profile from 2019 is used in the simulation load profile. Moreover, no modeling is done for constructural restrictions like those seen in gas power plants and CFPP. The findings demonstrated how numerous power plants need to operate more flexibility when they have a high level of VRE, particularly solar. The national hourly operation graph is an illustration of dispatchable technology fulfilling a residential load curve. The flexibility sources are still reliant on fossil fuel-based power plants in 2030. However, it is mandatory to decrease emissions through the JETP pledge, including reducing the reliance on fossil fuel-based power plants. まさに化石燃料に対するフレキシビリティはなかなか頼れなくなってくるんですね。Thus, it is important to consider how flexibility sources are evolving. One possibility for the dependable and suitable power supply is to switch flexibility sources from coal and gas to hydropower and storage ということで、まさに石炭ガスの調整力から、ある意味フレキシビリティってところがハイドロパワー、水力とストレージっていう蓄電池みたいなところに頼っていかないといけないと。The existing thermal power plants hold flexibility potential while keeping the asset momentarily due to limited internet in financing CFPP early retirement JTP CIPP profiles to pursue the coal phase down strategy. The term coal phase down strategy describes lowering the amount of coal used in coal-fired power plants by decreasing their utilization. From the technical perspective, lowering the utilization of CFPP is tricky due to technical restrictions such as technical minimum load. However, by lowering the technical minimum load (TML), the CFPP can offer additional value in keeping the power system running reliably at optimal cost. Additionally, CFPP can also improve the ramp rate and reduce its shutdown time to provide more flexibility benefits. Based on ISR analysis, operating the CFPP flexibility only slightly lowering the utilization of the unit. In total, flexible operation only reduces the annual generation by 9.5 terawatt-hour or 6% compared to normal operation. However, since the CFPP will be able to reduce its minimum generation and contribute more to the ramping capacity demand, an increase of 90%. The flexibility needs from other sources derived by subtracting CFPP generation and VRE generation from the demand curve will decrease. The graph of flexibility needs show that during flexibility operations, the graph gets less dynamic. まさにこれですね、CFB ピザ Hourly Operation Week 14 in 2030ということで、まさに1週間の流れの中で、この Increase Ramping Rate ということで、まさにこのランピングレートがガーンと上がってくるっていうこと。で、Flexibility Needs as CFPP Week 14 in 2030ということで、出ていると。Operating the thermal power plant's flexibility may lead to lower utilization for IPPs. The take-or-pay clause in the PPS serves as a fixed capacity payment that guarantees their capital recovery and fixed O&M cost whitelist ensuring system adequacy. Hence, no compensation is actually required to cover the lower utilization to a certain extent. The challenge, however, lies in the penalty for breaching some of technical clauses in the PPS as such as availability factor AF and heat rate should the power plants operate below certain threshold as agreed by both PLN and IPP. Contract restructuring is therefore required partially on how to incentivize services beyond capacity. Example, ancillary service and flexibility. While that is being solved, it is logical to carry out flexibility operation on PLN-owned asset. The Java Valley system will eventually be unable to meet demand on its own using resources. Interconnection could be solution and offering the flexibility potential. まさにコネクション、連携というところも一つの大事だと。Most of the dispersed RE sources are located distant from the demand center, making RE deployment challenging. It is difficult to move the demand closer to the RE resource since it is related to the economic activity. For instance, almost 70% of Indonesian demand is located in the Java Valley system, International Energy Agency. It will take long for the RE potential sources of this system to become inadequate. As Indonesia shifts to RE in the JTP scenario, the expansion of power grids helps to integrate the dispersed source of RE. The interconnection between the Java Valley system and other systems, including Sumatra, Kalimantan, and Satunggal, will help to bring additional renewable energy generation. As an example, RE interconnection to Sumatra helps to unlock the hydropower potential since the development of power system in Indonesia is constrained by reserve margin. Furthermore, Kalimantan and Satunggal offer a vast amount of RE potential that can be tapped to maintaining a adequate supply of Java Valley system. In addition to supply adequacy, improved interconnection has several advantages consist of increased system reliability, increased system flexibility, and load factors through the combination of various load patterns, particularly when integrating systems with different load profiles and optimizing the system operating profile. There are several risks associated with building transmission lines and must be considered. For instance, first, one, construction delays brought on the draw-out stakeholders negotiation and land acquisition. And two, PLN's limited expertise in HVDC island interconnection development. Therefore, as time passes, it is vital that advancement of these initiatives be given top priority in the year to come. The planned pumped hydropower storage project is set to increase system flexibility in near term, and more storage is still required to accommodate future VRE penetration. まさに水力と今度はバッテリーですね。Energy storage system ESS is expected to be one of the backbones of future power grid flexibility in Indonesia. However, the planned capacity of pumped hydropower storage PHES project currently stands at only 4.2 gigawatts. Despite this low capacity, there is notable progress in terms of construction, development, of utilization planning. Beyond its initial purpose as a peaker generation, the Upper Sisokam PHS pilot project is also expected to be used for spinning reserve provision, which will be relevant to the future grid flexibility needs. The country's first PHS with a target COD set for 2025 is still in the construction phase, specifically in land acquisition process. Meanwhile, the second PHS project seems to be progressed based on the recently published progress project financing proposal document of 4 by 225 megawatt Mategan PHS with estimated total project cost of 1.2 billion USD. Also, the planned capacity of PHS would boost the RE the RE share and increase system flexibility, it will still be insufficient to accommodate the required VRE penetration in the medium and long term. Taking into account the planned PHS capacity and excluding ESS for smoothing VRE output, IESR estimated that a total of 8.75 gigawatt of any load balancing ESS will be required by 2030 to allow 10% VRE penetration, aligned with the JTP pledge target. Furthermore, more than 132 gigawatt and 281 gigawatt hour ESS capacity will need to be integrated to achieve 100% RE share in 2050. Notably, this value is lower than IRENA RE 101.5 scenario suggested ESS requirement in 2050, totaling 448 gigawatt, including 116 gigawatt of PHS. The ongoing PHS development in Indonesia faces big challenges related to social and environmental issues, as most of the planned PHS projects are in Java, though in line with the current centralized electricity demand. The construction in such a populous region has a high risk of project delay. The land acquisition process is difficult, as can be learned from the Upper Sisokam project. The relatively high land cost and concern about the impact on natural biodiversity with endemic species also endangered in the island are also among the hurdles. Given the potential need to develop more PHS in the upcoming years, harnessing PHS greenfield outside Java with prerequisites such as inter-island interconnection should be highly considered for the future planning. While a large-scale PHS installation would enable more ambitious deployment of VRE, it is equally important to initiate plans for numerous small-scale PHS projects. These smaller installations, aside from matching the existing non-Java system supply demand size, will enhance local capacities for PHS construction and operations. To stretch the positive trends, government should encourage on-grid VSS deployment. VSS deployment has grown in the order of the megawatt, with more installation capacity has been announced for several VRE projects. It includes 10 megawatt hour VSS to support the Tana Laut wind farm that is projected to start operating by 2025, and the 8.3 megawatt hour storage in the IKN 15 megawatt solar PV project, the groundbreaking of which commenced this November. Moreover, there is ongoing tender process for 3,322 megawatt hour cumulative capacity of BSS in the phase one of the diesel conversion program that is targeted to come online by 2025. Recently, BSS integration on isolated hybrid systems and using Lib BSS has becoming more frequent. The 3 megawatt 1.84 megawatt hour BSS installed in Nusa Penida hybrid solar power plant system is an example that is often reported. The best system is used to support smoothing the output 3.5 megawatt solar PV. Meanwhile, with a different type of VSS operation, the installed 1.3 megawatt hour base charged by the relatively small 406 kilowatt solar PV capacity in the Bawe Island hybrid system worked as a peak gas power plant substitute. In both cases, VRE plus base integration is reportedly lead to remarkable fossil fuel use and emission reduction, and there are discussion to develop similar projects. Also, the installed capacity of BESS has increased and more advanced technologies have been adopted. Most of the implementation, including those in the pipeline, are still smooth purposes. There is a delay in BESS use, while global implementation for on-grid longer duration applications such as load and energy shifting have been gaining traction. and are expected to dominate the application mix of project shortly, reflecting on the throughout of BESS integration in the isolated hybrid system. It is necessary to immediately engage with research institutions to initiate several pilot projects on grid BESS with various technologies and types of utilization, as the construction and operation experiences will certainly help unbearable deployment in the future. Updating grid code and mandating ESS installation for new VRE projects would stimulate ESS growth and bolster market signals and technology producers. In addition, it may decrease the burden of grid operator expense on reliability costs due to the increase of generation intermittency. New standardization of storage requirements to support VRE integration will become increasingly important, with recently suggested VRE targets. Determining the exact storage capacity needs requires an in-depth evaluation of the existing power system. But studies indicate that for up to BRE penetration of 50%, which will be suitable with Indonesia's medium-term target, about 20% storage power capacity would be sufficient. It can be translated to the need of about 200 megawatt of ESS for each gigawatt VRE installation. Regulating the minimum storage requirements will also help technology producers to identify the upcoming demand, prepare their production capacity, and achieve economies of scale. In return, the fulfillment of future demand potentially become least cost. Currently, the identified demand by industry is relatively low. For instance, IBC projected base case battery demand for ESS is only 2.7 gigawatt hour per